Other questions? Then let's talk about forces. Chapter 4. No, yeah, 4. Too many textbooks, like different numbers. What is a force? Would you know if a force is applied to you? Stephanie, that was a yes?
Yes.
How? How would you know?
I guess, when you're moving or something pushes you,
You hit a key word right there.
pushes you.
Yeah, okay. Doesn't have to be a push though. What's the opposite?
Pull.
Yeah. So the best working definition is a force is just a push or a pull. The more formal definition is an influence that might cause acceleration, which I find a completely useless definition because first off, what's an influence? And the second of all, it might cause acceleration or it might not. You just can't, you can never tell. Well, actually, some in word problems, you can't tell. So, in essence, it's a push or a pull. So the way I generally do this is I start out with sort of the list of forces that we will deal with in this course, and then as we give it enough time, we start to chip away at some of the ideals and add in more reality. But this is the starting point.
This is chapter 4.
Chapter 4. Well, if you had bothered to show up on time.
The elevator took too long.
Elevators, do they make our lives any better?
They're scary here. It feels like they're gonna fall at any minute.
Oh, the one in Ardmore is something special. It goes like, going up, ching, ching, ching.
Final
And then-
destination.
And then you could hear, literally, you could hear the chords, ching, ching, ching. It's, yeah.
It's also a lot faster to walk up the steps.
We're so lazy in the morning, we can gamble it.
All right, so a push or pull. This is the checklist right here. Each of these stands for something. Otherwise, why write these letters down? F stands for friction. The symbol that I use for friction is what I refer as a Baroque F. Baroque. Sort of a fancy curled F. That's the symbol that I'm using for friction. Textbooks and other things might write something like that, force with the subscript F for friction. I don't feel like writing that much. T stands for tension. Now I used to use a capital T for tension because, well, that makes some sense, except later on we use capital T for period, and there is a formula that we'll hit near the end of the course where we do need period and tension at the same time, and so instead of just at that point going, all right, we've been using capital T for tension all this time, but now we're going to do something different, we'll just start out with something different. I do go the subscript route on that one. O is for other, because we need a catch-all, and I'll talk about specifically when other shows up, and I also wanted a vowel. N is for normal, and G is for gravitational. They're nouns, they're adjectives, it's not parallel. Just deal with it. Except I suspect I'm the only one who would actually care. Anyone bothered by that?
Most certainly.
Okay. Ibrahim and I are the ones who were bothered by it. Now, the symbol I use for normal force is a capital Y, which is also a homophone of perhaps a question you're asking. My high school physics textbook used a capital Y.
Why?
We also don't use capital Y for anything else, and so it's very convenient. Now, some textbooks will use a lowercase n, which is also the symbol for nano. Some textbooks, and some students will use a capital N, please don't. And some will do F subscript N. Here's my big issue with using capital N, is that capital N is also a Newton. A Newton is a unit of force. We just defined 1 Newton is, by definition, a kilogram meter per second squared. So if you're using capital N, then the following would make sense in physics, that N is equal to 3N. This says that the normal force is equal to 3 newtons. In math class, this would mean that capital N is equal to 0. So these two N's in physics would mean different things. And so I'm really not a fan of that because it does show up, but we can't help it later on in 152. So don't use the capital N, and let's go ahead and put the Mr. Yuck sticker there. Don't do it. In context, I know what you mean. However, it's just bad practice. All right, and then gravitational force. There's actually 2 different gravitational forces. There's the one that we will deal with until we get to chapter 6, I think it is. Weight. And then there's a general gravitational force. And I do go with the subscript again. F's a little g, and this is the generalized gravitational force, or force due to gravity. Now, you can always use the more generalized form of it, but it becomes a real nuisance because there's a much shorter way that we will deal with it most of the time. And unless you, well, in physics, we do deal with celestial bodies orbiting. In your everyday life, probably will not be using the generalized form, but we'll do it in here, just in case. Now, other. It's a catch-all. Other is when, well, let's actually talk about requirements, and that perhaps will give some light into other. Other is when you don't know or don't care, and I'll modify that in just a moment. Don't know or don't care what the source is. And I will write up in Word English. Don't know or don't care the source. And when I say don't care, I'm not talking about your own personal philosophy. It's a matter of, is it relevant to the actual problem you're trying to work about whether it matters. For example, a box has a 5 Newton force acting on it. It really doesn't matter what is causing that 5 Newton force, so that would be an example of other. Other generally shows up in a problem. It's some unknown or some strange force that's showing up. Or when you get a little bit more sophisticated, you can start to make start to go through and decide, okay, I really don't need to know that. We're not there yet. So it is problem specific. The symbol that's used really is problem specific. All right, friction, a requirement. Contact. Friction is not, we're ignoring air resistance. Where friction depends upon, well, first off, two objects have to touch. There is no friction between me and Stephanie. Because my Jedi powers are not working at the moment. The other requirement is that there is desired, with that quotation marks, desired relative motion. What I mean by that is, if it were frictionless, would it move? So right now, if the carpet underneath this table here were frictionless, would the table move if, as is? Is there any reason for it to start sliding?
No.
Probably not. So there's no desired movement. If I push on it and it were frictionless down there, would the table move? There's now desired motion. And by relative, it's relative to what it is touching. So it's not a matter of whether this is going to move relative to a car driving by, it's whether it's going to move relative to the carpet. I got a block of wood, and a marker on it that potentially will stay. If I move that way, if the block were frictionless, and why don't we pick something that's not going to roll as much? If the block were frictionless and I move that way, what would the pencil do?
Move that way.
It would move which way?
The direction that you, direction that you move it to.
So if this were frictionless and I moved that way, the pencil would go with it?
Yeah.
Why? What would cause it to go that way? Again, Jedi powers on the blink.
Probably.
The air. Well, we're ignoring air resistance, but
God did, sure. I think that, you move that way. Are we assuming that, like, the pencil's gonna, like, are you moving the block with you?
I'm moving the block with me, yes.
Or the pencil is most likely going to either roll off or move with you. Because it is attack, or it is on said, block that you're moving. However, if it's frictionless, then it might just levitate, or not levitate. When you move, it'll be like that.
So, in essence, you're getting closer there. If it's frictionless, then what's gonna happen is the pencil would stay where it is, and the block moves, and the pencil would then fall off at some point. That's relative motion. It's not whether the pencil's gonna move relative to the ground, it's relative to the block. So from the block's point of view, the pencil's gonna go that way. So friction would act opposite that. So friction acts on the pencil in that direction. So that's why when I move this way, the pencil goes with me because friction is causing it to go in the direction I wanna go. I'm assuming you did not play with frictionless objects when you were growing up. There's an ad for a timer years ago that advertised itself being frictionless. I was like, how can you make that claim? Especially when you're advertising to physics instructors. Anyway. All right, tension. There are basically two types of tension. Tension's a pulling force. So the requirement is, as far as we are concerned at the moment, a taut or tight. The only reason I got stuck on the word taut. Rope, that is the view there. Rope, chain, during whatever happens to be pulling. Normal force requires contact. Gravitational force, the generalized, is just two masses. There's a gravitational force between you and every object in here. It is an incredibly weak force, weak with the lowercase w, not an uppercase w, because yes, there's a gravitational pull between me and this container, empty container of Expo board cleaner, but I can easily walk away from it, and it's not dragging me back in. And I would suggest insert your own Al Pacino imitation from Godfather 3 at that moment. And if you don't know that reference, probably should watch Godfather 3. Which is generally good advice anyway. Weight, it still requires two masses, but the difference is in this, the two masses, you have one huge mass and one small mass nearby. So I got huge and small in quotation marks because the size is somewhat relative, but huge, I'm talking planet size, something like a planet or a moon, something of that nature, and small, an elephant would be considered a small object here. Mass of the Earth, for example, is about 6 times 10 to the 24th kilograms. So if you're having to express the mass in times 10 in scientific notation to make it easier, it's probably considered huge. I know it's just basically vocabulary at this point, just words. We will start to show application at some point. But any questions at this point?
Will we continue to use cake formulas, or are we gonna start using, new formulas?
All right, so the connection is, and for some, did I actually hit record? Yeah. Physicists would love to be able to teach chapters 2 through 5 all at the same time. It's difficult to do. Chapters 2 and 3 deal with describing motion, and acceleration is describing motion is specifically position, velocity, or displacement, velocity, acceleration. Then it comes down to what causes acceleration. Well, forces cause acceleration. So now we sort of, it may seem like we're starting from scratch here, but ultimately we're going to connect this with what we've already done. So will we use those again? Yes, we will. We're now concentrating on forces, which will lead directly, which will connect back to acceleration, which then launches into everything we've done so far. And then we'll get to a point where we go, you know what, let's look at this differently, and we'll bring in energy. And then we'll go, you know what, let's look at a different way of looking at the exact same thing, and then we'll talk about momentum. That in essence is physics. I assume that was a sound of excitement and not a yawn. All right, any other questions? Or the same question if I didn't answer it.
So,
No. All right, so 2 more columns to go. Next one is, because all forces require, well, let's do this other one. Forces always come in pairs. And there's not a lot of times in physics where you can actually legitimately use the word always, unless it's a definition. But this is one of those things. Forces always come in pairs. There's one tiny little exception, which is well beyond the scope of actually even my graduate studies. So I'm still going to use the word always. we can be more specific, because since for every force, there's gonna be another force. They come in pairs, the two forces are of the same type. They act on different objects. And they point in opposite directions.
That's an always.
Yeah. For the sake, until you get, I probably should have learned the basics before I talk about the one rare exception that has never actually been seen, but theoretically is possible.
But if you're moving and somebody pushes you,
You're pushing back.
huh?
If you pushed on me right now, first of all, sorry. How do you know if a force is acting on you? What is one way to tell if an force is acting on you?
Contact.
Well, how do you know that there's contact?
You feel it.
Okay, so if you pushed on my arm right now, abuse, did you feel that?
Yes.
Yeah, that was my pushing on you. You pushed on me and I pushed on you at the same time. That's what we're talking about. So you applied a normal force on my arm applied a normal force on your hand.
Oh. Interesting.
It is. All right, so when we're doing force diagrams, which is coming up, when we're doing force diagrams, we're gonna draw we'll draw the forces, we'll draw pairs of them unless there's an other. And forces that are causing things are basically pulling forces. The arrows, when we draw them, will point towards each other. And this will become abundantly clear in probably about a half hour.